Okay, thank you very much, right, Professor Sang-Ram, for inviting me again. So I'm also very happy to see you again. Today, my topic is like Mattila-Sjölin type functions. So what is that? I will explain this meaning later. Okay. So today, I wanted to talk about two things. So first, I wanted to review the finite field Erdos-Falcon distance problems, and then second, I wanted to introduce good distance function. What's the meaning of good distance functions? So you will know later, okay? So this function gives us good distance result. We can prove it, okay? So this is a very famous problem now. It's tough. No one get right conjecture, but for certain specific good function, we can solve this problem. Okay. So actually, the second thing is my goal. I mean, I wanted to introduce new distance function, right? So if you study this kind of distance problem or properties, maybe you may get some idea to get this conjecture. Okay. Who knows? So let me start. So let me introduce what is the Erdos-Falcon distance problems in finite field setting. So let me visualize this. We are living in this finite field space. You know this notation, right? FQ is a finite field with a Q element, right? This d-dimensional vector space over finite field. So now here is vector x coordinate is x1, xd. Here is another point, right? Now we have set E. We take arbitrary set, arbitrary subset E, any set, right? Then now we define certain this notation. Looks like normal of x. What is that? x1 square plus xd square. This number should be in FQ, right? Here there is no square root, right? That's good. Now we are living here. We choose any 2 points in FQD. We want to get distance, right? What is distance in this space? Like, let me define the distance function. Looks like a matrix. It is not matrix, but this looks like function on FQ2D, FQ2D. This is a finite value function. Okay, this distance function defined by. Let me get this distance from x to y, like define. Just we using this notation, right? It's natural, right? But here there is no square root because this is finite field. Now let me define some. So given subset E, right? This is not empty set, right? Empty set, right? So we choose any 2 points, we get distance, right? Many distance, sometimes few distance, right? So we collect all distances from set E. So we define the certain distance set. Actually, this notation is distance from E times E. You plot E. Collection of this all distance such that x and y and E, right? This is called distance set. Actually, this set, right? So any set makes this kind of set, right? Distance set. So shortly, we use this notation. Okay. Not Next, let me note it's a cardinality of E, right? Cardinality of E is natural, right? Trivial, right? If the E is not empty. How about this cardinality? Distance set cardinality is look at it is always true, right? This set is contains 0 from 0, x to itself, right? The distance is always 0. Right? So this is not empty, so this is 0. So you may this is naturally subset of this F2, right? So this cardinality is this cardinality is Q, right? Q cardinality Q. That's right. So it's a trivial. I mean, you may guess that you may expect that if size of E is increasing logic, and maybe size of distance set is increasing, right? But this is maximum value, this is value, right? But this is, here is a natural question. Split is Ludnip 2000, I think at that time 5. In this year he posted on archive this version. Okay, there are many versions of distances, right? The first time maybe in finite field version like Bolgain and Koch and Tao, they considered. They wanted to understand the relation between size of E and size of distance. But now, today, I'm not interested in such kind of Erasmus. This is Erasmus problem. Today, I wanted to focus on different way. This question: what is that? How much bigger set? FQD, right? Do we need? What is the conclusion? We have two conclusions. What if this size is FQ? What does it mean? This distance set contains all distances, right? All distances. Right? This is conclusion. So, how much bigger set? This set is arbitrary set, right? Its natural trivial answer is like the size of E is like FQD, whole space. This true, but we need to find the small, right? Smallest size of any set, right? Okay. That is a question. The second version, we make a weaker conclusion. So not everything, but this distance set contains almost all distances, like that similar cube. We have two conclusions, right? So we have two questions. What's the meaning of similar? Yeah, it's right. Equivalent, right? Like this. Like C1, C2 right here. For some, right? Uniform constants. So this first problem is actually this problem was called Erdos-Falconer problem. But actually, strictly speaking, there are two versions, right? In terms of this conclusion, right? This is one problem. This is actually the other problem, right? So this conclusion implies this. So today I distinguish these two problems, okay? I call the first problem just the Mattila-Sjölin problem. Okay, Mattila-Sjölin problem. Let me write down like that. Mattila-Sjölin problem. Okay, this question. The second question, I call this problem as just the Falconer problem. Okay. So Mattila-Sjölin, this conclusion, the conclusion on this Mattila-Sjölin problem imply the result of this Falconer problem, right? Okay. So let me write down the formal definition of these two problems. Okay? Formal definition. Sorry. Okay. I can use that. Okay, question. That. Okay, C is a large constant, okay? Like tell me. The smallest constants alpha real number such that if the size of E is much greater than uniform constants which is independent of Q, alpha imply the distance is contained all these distances, right? Okay. Now this question is called Mattila-Sjölin problem. Okay. Yeah, it may depend on D. D is okay, but I suppose the large constants, right? It may depend on D. Okay. Okay, our parameter is always Q. Okay, we send the right Q infinite later. Okay, so Q is always parameter. D is like a dynamic, right? Constant. We fix D. We change the finite field, right? Any finite field. Now, Falconer, what is the Falconer problem? Falconer problem is just replace this one, right? More weaker conclusion. So our distance set contains almost all distances, right? Almost all distances. So this problem is called Falconer problem. Suppose we did not distinguish these two problems. Just this problem is called Erdos Falconer distance problem, right? Now, which problem is more harder? This Mattila-Sjölin problem is more hard, right? To get sharp result. Now, natural question is what is a conjecture? What is known, right? Okay, before I introduce this conjecture, let me write down known result, right? First time. So Yoshevich and Rudoniv, the same paper, they proved that they actually did not mention about this constant, but I computed like that. 2 is enough. But many people claim that this is 4. Actually, 2 is enough. E is an FQD, right? Then strong result, strong conclusion, right? This is the first result for Mattila-Sjölin problem, right? Also, this is result for Falcon problem, right? Yeah, all Q. Yeah, Q. T is fixed, right? First T is fixed. Yeah, Q is parameter. Whatever parameter this. Even D2 is independent of D, right? But it doesn't matter. But for this problem, we are not interested in the dependence of D right here for constant C, okay? But here, fortunately, we got uniform constant. Okay? I mean, point is this constant must be independent of Q. This one. This is a Mattila-Sjölin problem, right? Result, right? Now, so far, 2001, right? It's 2021. How many years? I think no one get new result for general set E, right? Even prime field. No one get it. For Mattila-Sjölin problem, okay?
Construction, like what would be the best that you could hope for?
Who?
What's the best that you could hope for? What's the best construction of it?
Yeah, I'll introduce. Okay. But this is known. But let me explain later, okay? But it's right. It's a Falcon problem, right? I mean, okay. It's first time. It's always named right, which maybe at that time many people studied, right? Yeah. Okay. But here. Okay. Dimension 2. Okay, 2 dimension. Also, then we get height proportion over all distance. So look, if D is 2, right? This exponent is so 2, right? Actually, our conjecture is we want a D over 2. It's conjecture, right? We really wanted to get D over 2. No, for certainty, yeah, certainty. I will explain it. For other dimensional, this is sharp O. I will explain it. Okay. But this exponent improved only in 2 dimensions, but conclusion is still weak, right? Falcon problem. So strictly speaking, this Mattila-Sjölin problem is it is only result for Mattila-Sjölin problem. Okay, result. Okay, only result. But little bit in 2 dimensions, this exponent is a little bit improved because this is smaller than third of 2, right? So, but this conclusion is not for Mattila-Sjölin problem, right? Even people, like a lot of people got this one, even learned, right? You got much strong conclusion. Pin distance version. I mean, I will not talk about pin distance version, but originally we got using Fourier decay, we got this one. So other guy used a certain group action. They prove again this one. But learned group is prove this result, but the result is much strong. I mean, pin distance version, not this version, but pin distance version, right? Then what is a conjecture? Okay, we have 2 conjecture, right? For Mattila-Sjölin and just Falcon conjecture, right? But I strongly believe most case 2 conjecture are same, except some few case. Okay, so let me introduce what is a conjecture. in some recent paper, right? I mean, conjecture was mistake. I think missing one part because of some error, right? Nowadays we can fix it, but let me introduce correct conjecture. Right? Correct means is better conjecture, right? So that's the fact, known fact, right? D plus 1 over 2 exponent, right? This exponent. Sharp. Other dimension. All other dimension. Or other dimension, right? Not even. Except. Possibly except. For k minus 1. K is integer, right? And what is Q? Q is modulo 3. Q is 3 modulo 4. I mean, which mean is minus 1 is not a scale number. Not a scale number. Right? We missed this case. Like there is some mistake. When you consider counting example, this proof is not complete, incomplete, right? So far, we believe now it is open, okay? We still get there is some possible to improve this for this case. But other case, in other dimension case, the plus 1 or 2 is sharp. Even for sharp, even for Falcon. Sure, this the Mattila-Sjölin version is sharp. But moreover, this exponent is also sharp for more weaker version, right? It is constructed, okay? However, the dimension even, still, we believe this we can improve. So now another more P. Recently, this, right? I think 2019, they construct some example. They found some set, many set. Two-dimensional set, right? With the minus 1 is scale number, okay, such that cosine and this set does not cover all. This set does not cover all distances. So in general case, two dimension, this exponent is cannot be improved for Mattila-Sjölin conclusion. Okay, but this conclusion is still we have a possible to improve this exponent for Falcon, right? So now I'm very confused. What is the conjecture for Mattila-Sjölin problem? I'm very confused because we cannot get d over 2, right? Because of this example, we cannot get d over 2 for dimension only 2, right? In specific case. But still, if the Q is 3 modulo 4, maybe I believe d over 2 is conjecture. Okay, so let me state my conjecture or our conjecture, right? I believe, someone believe, right? The first, let me conjecture for, okay. Okay, T is even, and Q is modulo 3, right? We must exclude this example. Either or D is odd, right? Okay, minus 1 and minus 1 is not a scalar. The same thing. This is a conjecture for Mattila-Sjölin problem. Okay. So what if the Falconer conjecture, Falconer problem conjecture? I think we don't need this assumption, right? For Falconer. For Mattila-Sjölin problem, we must need this assumption. Because this example, but this is not counting example for Falconer problem, right? So recently, the Falconer problem is okay. Mattila-Sjölin problem is now Iosifovich Rozhnev say result is that's no result, but for the Falconer problem, right? As I told you, right? I mentioned 2, right? So we got Poisson. Now recently, so many people, the Rozhnev or something like that group, there are so many people, right? Sorry, maybe I think 2000 last year, right? They got this one. Okay. Okay, let. It is a prime field, okay? Prime field. Not general field, prime field, right? They improved for sub. Like that. 504. Actually, the pin distance version, but they improved this one. 504 is much smaller than this one, right? But this is works only for prime field. For general field, no, right? No. So there are 2 conjectures like that. I think you can improve this any this result, right? Any previous result, right? You can publish, right? The result, at least good, right? Alright, so I'm stuck, right? For many years, right? We try every day. I think about this problem, how to improve this one. Now there is some skill how to get this kind of problem. There are 2 skills, right? One skill is for Mattila-Sjölin, the other skill is for Falconer skill. If I have a time, I will introduce a rough idea for how to get this Mattila-Sjölin problem. Very roughly. If I don't have time, let me skip the idea. But now, in remaining time, I will introduce new distance problem so that I solve this conjecture for certain case. Very interesting, right? So let me generalize distance. Before I introduce my good distance function, right? Let me define something. Again, right? Natural number. So I'll take dimension d is always even, okay, even. Okay. So let me write down this vector is like that. First, the half coordinate is written by x prime. The other half coordinate is denoted by x2 prime. I mean, I write down this as like that, f of q. Actually n, right? d of 2. So y is also y prime, y2 prime. Okay. Now, let me define distance pi. Looks like a distance function. I will define this function. By take two vector, right? I call this function is distance, pi distance function, right? From x to y. If this is usual distance, what happens? This is like that, right? This usual, if the pi is usual distance, right, we get this value. But this value is, looks like, if we use this notation, what's the distance between this and this vector? We may get this distance, plus x2 prime minus y2 prime. This is distance between distance in d of two-dimensional, right? Distance, right? It is true. You can check easily. But now I'll slightly replace this distance by like that. I don't want to add this term. I wanted to divide by this term like that. So I will define like that. This one is difference first half the difference of the first half coordinate divided by, and second is like there is a reason why I got this one. There is a strong reason. That's research, right? Yeah, I had a feeling if I define like that, we get good distance, right? But this is not well defined. But the bottom is not zero case. Otherwise, zero. Zero, right? Otherwise. Okay, this is a well-defined function, right? This is the function. Let me give you a definition. A function, like first side, a distance function, a distance function like that, is called Mattila-Sjölin type function of index gamma. What is the definition of this? This gamma number is the smallest exponent, right? Smallest number. Such that if it is put QD with the size condition, right? Much like then QTD what? Gamma, right? This set imply pi distance set, right? Let me write down like that. This pi distance set, right? Yes. Cover all distance. So here, gamma. What is definite gamma, right? Gamma. The smallest number, right? Usually conjecture for distance.
Is it supposed to be psi in both of them, or
smallest number? Oh, gamma is smallest numbers. Satisfy this condition, right? Many gamma, right? I mean, how can I get?
I'm just curious.
Oh, sorry about. Well, general case, the other thing, right? I will replace by this psi pi. Okay, later, like pi is our function, right? Actually, this well, today my claim is that this pi function satisfies this gamma function. What is a gamma? D of 2. Some case D of 2. For certain assumption, gamma is something less than D of 2. So yeah.
Show exactly what this.
Yeah. Surprisingly, with our pi function, I answer all gamma. I got sharp result. Very interesting. Computation is almost equality. So we can count exact number of distance, cardinality of distance set. So we solve all conjecture. We can construct count example. We can solve conjecture. Actually, we know worst case of set, right? And then we put the 1 point. Then we get this. So what is the theorem? Our pi function is right. Our pi function here is the Mattila-Sjölin type function of D of 2, index D of 2, right? If and only if, interesting, right? T is exactly 4 dimension, and -1 is not a square number. Why? So without this function conjecture is wrong, except for some specific dimension, dimension 4 or something. We only get D of 2 here for this pi function. In this case, other case we get work result, work gamma, weak gamma, which is sharp, right? So before I state our result, let me introduce why I consider this one. If you know some skill how to get to like a Mattila-Sjölin type problem, maybe you understand. But roughly speaking, this relate our pi, right? Our function pi, coup function. But usual function relate to like that. If this is t, this function have t value, right? T distance, right? So we want to count, first the idea is fixed t, right? T is not 0. If we prove that there exists some point in E such that the distance is t, then which means t is arbitrary, right? T is arbitrary. If we can prove that, assume that we prove this one, then what does it mean? Our the distance set of E contain t, right? So t is arbitrary. So we distance set get all distance. This is ideal. So people just estimate to number of this pair such that this is true. First fixed T. This is original idea to prove the Mattila-Sjölin problem, right? And the other thing is like I don't want to explain the technical issue, right? So but basic idea is like that. But same thing to solve this Mattila-Sjölin problem, we put this T, right? Fixed T. So we want to count, right? Pair of this number, right? Such that this number is T. If T is not zero, right? Bottom is not zero. But which one is the hard form? I think this is more hard form, right? Bottom and something. This is like just one single term, right? But why this form is good for me? But it multiply like that, and move to that. Then what happens? This equation is equivalent like that. Minus T times. We have this variety, right, equation. But this is not nothing but homogeneous degree 2. It's cone. This contains a lot of line. Usually this kind of variety gives us weak, very weak conclusion. But except for this case. We know how to compute it. But what is the good news for this variety? We can compute the right explicit value of Fourier transform of this variety, like cone. So one day I knew how to get the explicit value of Fourier transform cone, but it looks like cone. Then our computation is very explicit value, right? Then we can compute. But in this case, even if you move like that, this is not right homogeneous variety, right? This constant. If this T is not zero, right? Then this variety relates to a certain Kloosterman sum, which is very hard to deal. So I slightly change this distance by distance. Non-security works, right? I mean, recently I studied the cone, right? Last talk I gave you a talk about the cone restriction theorem, right? In that case, right, Fourier transform of cone, explicit value of cone, Fourier transform works very important. So recently I also thought about this distance, right? Then what is the non-result? Our result. Actually, I was surprised with this result, our result. Why? Let me explain. Theorem 1, this case, if dimension is 4, right? Dimension 4, minus 1 is not a scalar number, and is 4 dimension, this case. What the size? Any size? Actually, what is conjecture? D over 2, right? D over 2. D is 4. So 4 over 2, right? Conjecture exponent 2, right? Yes, 2. Okay. Now, surprisingly, we have this. Coefficient C is 1. It's really sharp, right? We can construct, right, this current example, whose size of E is like exactly Q square. I was surprised this because the computation is very explicit computation. We got explicit computation, right? So I was surprised with this. I have never seen such a kind of good constants, even, right? Yeah, moreover, then is what? Now, pi distance, right? I call it usually a quotient distance. Quotient is like quotient, right? But you may be wondering, well, what if? How about other case? Okay, dimension T is even, right? according to my construction, right? T must be even. I mean, you can generalize, but now, how about other case? As I told you, if for other case, it's impossible to get P of 2. A sharp result is worse than this. So what is known is like that. Okay, let first case. This is a 4K multiple of 4. Okay, and this is big C. In general case, then we get pi distance set cover all distance. You can check this is bigger than P of 2, okay? But this is sharp. We can give a split count example. This is sharp. We cannot improve this. I mean, we may improve these constants, but now, moreover, let us assume more, okay? If here K equal odd 1, 3, right? K equal 1, T is 4, right? And -1 is not a square number. There is no I. There is no I element. Then we can improve this one. Let me say this exponent gamma, okay? So here gamma is -4. A lot of improvement, right? It's enough. Enough to get this conclusion, right? This. For example, K equal 1. What happened? K equal 1. K equal 1 is, in this case, T equal 4, right? K equal 1, T equal 4. -1 is not a scalar number, right? We get this exponent is 2. This previous result, right? This is a more general result. How about other case? The other case is also, now another result is like, what if T equal even 4K plus 2, right? This is strange, but this is all case, this is sharp. 3D minus 2. Middle case. High distance cover all distances. So this is sharp. Whatever Q is, Q is not a scalar number, -1 is not a scalar number, or not, Q is modulo 3 or 1, does not matter, right? This is sharp. We can construct some count example. This is sharp, right? This is sharp.
So you have for every D and for every sufficiently large Q, you get the correct.
Yeah, correct. It's surprising, right? If I put this assumption, we get this one. In other case, we get this. And for each case, we can find concrete count example. But yeah. Yeah. Okay, so its distance is, I call distance is good distance. Because it's a distribution of distance is very well, right? Well distributed, right? Our pi function makes distance well distributed, right? No, but anyway, we figure out all property of this pi distance. But without the original conjecture is wrong, because you according to this distance, right, only d equal 4, specific case when, right, q is 3 model 4. In this case, we got conjecture d over 2. For other case, right, it's impossible to get d over 2. What the problem? For Mattila-Sjölin problem. So I thought we need to change the conjecture for Mattila-Sjölin problem. I still believe now the conjecture for Falconer problem is true, but I'm doubt the conjecture for Mattila-Sjölin problem, right? D over 2 case, right? Some specific case. Sometimes it's not true. Look at this example. Only d equal 4 cases, the conjecture is true, right? So finite field is very strange because it's because of this certain q value, right? Structure. Finite field is unusual.
It's also, so it's only in this special case that you get the kind of 1/2 the exponent. We already know d plus 1 over 2
is true.
Is true. Is a
that is okay.
For all dimensions for the original normal quadratic form.
Yeah.
This
This is this. Yeah. This is sharp case, right? General case. Okay, that's a good point. Yeah. There, let me see. This case, like, it's Colorado. Let me say Colorado is interesting, right? You're right. That's a good point. I'm very happy if this is true, right? It's impossible. It's impossible, right? Because of counting example of the construction of the Morpheus and Pettinus, right? But this is true. I'm not sorry about it. Look at, you understand, right? Because it's quotient function, right? This is nothing but take is a times a. Our previous result, this case, right? D equal 4. Coefficient is 1, right? So if you take this, then you can check this is nothing but, if A is not empty, this cardinality is same as this, right? How much is A times A, right? E times E. The quotient, right? This gives us this. This gives. So what's the corollary? This implies it's trivial. This size is because it's a right? It's divided by like that. Otherwise, we cannot get this. Useless, but actually, counting example is very. There are many ways to construct counting example, but easiest way to construct counting example is like that. Very, very easy. Take E is like that. In general D case. Now half coordinate is just 0. I mean single value. Then you can check, very easily check, size of E is Q to the D over 2. What's the distance? Pi distance. Only 0, right? Because second coordinate is have only one element, right? This is this gives our counting example, right? So must be right exponent must be greater than d of 2. Look, as you see, right, like that. That is the case. Especially d equal 4, we get if we put one more point here, we put the one more point like that. This certain a, right? A not in here, right? Not the FQ, right? It's surprise. Surprise. It's a pin distance, like looks like pin distance. You may think of pin distance. But in dimension D, we last observation is that is our condition, right? Cannot be dropped. For our sharp result, right? Dimension D equal to D result. Dimension D is 4, Q is 3 modulo 4, then we get D of 2, right? But we cannot drop this assumption. Why? Otherwise, we may take Q is 1, right? Modulo 4. Otherwise, then there is I, right? Such that scale number is -1. Then what happened? Take E. Very easy, like half D of 2 times what kind of set? Not singleton, not a single. We put more T times IT. 2-dimension variable, right? So T in FQ. You may choose any 2 elements and then you can measure, right? Distance. This is only 0, right? This bottom. So take this. So E is exactly kinode of E is this kinode is Q, right? Q3. But we cannot get all distance. Just 0. So it cannot be D over 2, right? So every statement is sharp. We can visualize this problem. We can completely understand this problem with this good function. So it may interesting if you find another distance which gives us good function. So you may try to find the connection, this Q distance and original distance, right? Problem. Right? Q distance, right? Okay. Yeah.
Is it necessary for your method to split the coordinates up evenly into, like, the dimension is even and you have n coordinate distance on the top and n coordinate distance on the bottom? I mean, if you split it in any way, you'll still get a homogeneous equation for your cone, or you still get a cone.
For general homogeneous product, I cannot get the explicit form. I cannot get Fourier decay, but not because actually we need to get explicit form of Fourier test form. In fact, I use sign. Look at. Audience is not happy with it. Distance T, fixed T. Define counting function. What is VT? cardinality of pair x, y in E times E such that any distance function, right? T. So note, this cardinality is positive if and only if our distance function generated by E contain T. This is general idea. So to prove this is same as FQ, our goal is find the minimal size, right? Size of E such that we fix T, right? For T is positive. So I task is just compute this one, right? Which depends on T, right? I mean, actually depends on E, right? Definition of VT depends on E, right? So the both Falconer problem and Mattila-Sjölin problem, this VT is very important. But now now this method, this idea is just for Mattila-Sjölin problem, right? That's why we get this T distance. But the certain Fourier analysis, right, gives us these cardinalities. We want to count this pair, right? So we want to sum certain condition x, y in E. We take some summation variable. It's a condition if the x, y is satisfied this condition, we count 1, right? Otherwise it's 0, right? I mean, this is nothing but set, right? Set, like picture, like nothing. We can do that. But this is like mathematics summation. But still, this is ugly, right? For the analytic number theorists, like deal with this kind of sum very well, especially when dimension is high, the higher dimension, right? So they just get this is like everything like that, replaced by this one. Not true. This is indicates function, right? X may here indicates function. But still it's different, right? How can it deal with this condition? Should be this right? How can it deal with this condition? Characteristic function, right? Some x2 variable, right? Such that x, y satisfy this function, right? So usually idea is like that. There are many ideas, but here we consider this is a very difficult part. RT okay. I think this looks like norm. Get oh no. Sorry about this. Look, you think this is like norm? No. Distance between two, right? Norm is T, right? What is that? Sphere. Whose length is T, right? Like looks like sphere. No, yes, yeah. But we define this one, right? But this condition is like that. X minus y. This distance, x minus y, right? This is same as Just so your idea is like that. It's actually no, it's not. This is the shape. You can just compute using formula, Fourier inversion. So very easy, right? Then you can choose any points. Then you met hard part, right? But fortunately, my good function just gives any hard case, right? Then this is characteristic function, right? This guy is living in our space, right? FQD. Now Fourier transform, right? Fourier transform space, right? Space is dual space is another place. Fourier transform space, right? Like one-to-one correspond like that. You may head, right? Here, what is that? Okay, correspond. So let me use your skill. Change all this form, this space, right? We move to Fourier transform space, like. So Doowon became something different guy, right? But looks like same guy, essentially same guy. But if I go to Fourier analysis space, right? Maybe my shape is different, but its original property is same, right? So essentially, what is that? This space is actually dual space. The functions, right? Characteristic functions, Fourier transform. Never mind, right? This guy is Fourier transform. The last time I introduced Fourier transform, I got this one. Always, whatever phi is, we get this one. Because this is a person, right? This is another person. If we change this one, if we change this one, we need to change this one, right? If for the usual distance, this is a sphere. Like sphere. Which radius t, right? For the usual distance. This we replace by this for usual distance. For our good function, we have this Fourier transform. But you can check this in real term. This is very explicit, right? If you here m is 0, m is 0, this is always positive. We know. So you can split some two parts. Main part is positive part, remain part. To get this positive part, usually we use m variable here. Whatever m, this is whatever set is, this is to the d divided by cardinality of RT. Is known. So whatever this set is, we get explicit value, right? That's no problem if m is 0. Positive. This is also set, right? Positive. Like this form, right? We replace this by this. So if m equals 0, this general term is always positive. Positive value support us, right? We want to show that the it is positive. So for the usual distance case, we only know when this is positive. Only m case, m is 0, we know this is positive. But for this, our good distance case, for other m, most m, this is positive. Right? Because we know this explicit value. So we get big positive, big negative, something like that. Minus some blah blah, plus blah blah. We know this is positive, right? So we want to get positive, right? This is our. We don't need this estimate because delete positive delete, but still we get low bound, right? Low bound. Now find some size conditions such that this is true. We may get this explicit value, which written by in terms of size of E, right? Then we can choose size condition. This is ideal, right? This is a huge ideal. But surprisingly, this I need to point out. yeah, okay. Because finally, let me just say this one. For you one, right? It is positive, right? Okay, if in this case t equal 1, we know positive, right? Certain if t equal, okay, so q square, right? Let me say t equal 4. T equal 4, right? We know this one, right? We know this one. We prove already, right? Any t, actually any t, right? Any t, right? But now choose one. So for the Mattila-Sjölin problem, we want this value is big, positive number, right? But what happens if you estimate the following fact? If t equal 1, this is small, very small. Negative does not matter. Negative impossible, right? Then you solve a usual distance problem. Why? Why? Look, roughly speaking, this is what? Number of pair x, y in E. E is A times A, right? Such that, let me remove t, right? I could x minus y prime, 2 prime, 1. Sure, this is not 0, right? That's it. Now we can deal with that case very easily. But this is same as, right? Separate this word. X prime, y prime in A, right? Such that, what is that? X 2 prime, y prime, x 2 prime, y 2 prime. And you are familiar with this one, energy. When you attack the usual Falconer problem, which main estimate, what is the main estimate? Falconer problem for this set, it is well known. We want to get good upper bound, small upper bound. Once we get small upper bound of this one, we solve Falconer problem. But for this problem, this y1 is small, right? Positive. I believe y1 is small. Why? No. Yeah, it depends on size of A, right? Okay. If you study, right? If you want to do the Falconer problem, right? For this set, main estimate is just try to get good upper bound. Right? Trivial upper bound, what? Trivial upper bound is A post, right? Improve this one like that. Once you get good upper bound in terms of A, you get new result. This is the main estimate for Falconer problem in dimension, this kind of dimension, right? But our problem, if we estimate y1, right? Actually, we want that this y1 is small, right? Even yt is small, right? Large, right? So that this is positive. Then we are happy. But the five-corner problem, we wanted to get this is a very small. The both problem are distant problem, but one case I wanted to get big number. The other case I wanted to get small number. I hope this is small, I'm happy. The other problem, if this is big, I'm happy, right? It's very strange, right? Both problem are distance problem. Why this is happen? I think about this one because this is the one, right? I assume V1 is very small. Why? Already you got Vt is positive, right? For all t is positive, right? So specific one is small. Okay, let me finish, right?
Yeah.
Sorry. Maybe it's so late, right?
Yeah.
I waste my time. Personally, you can ask me.
Yeah, that's pretty good. Yeah, let's finish. Thank you.
Actually, I wanted to let